bombarding you with recommendations on that. Right? Of course, every once in a while, these recommendations tend to be off, right? Sometimes it tends to be a little too much. But the important thing is that there's something that's powering, these algorithms that make it such that you don't have to sweat over making a choice. Because honestly, when you are bombarded with too much options or too many choices, making a choice can be very difficult. So decision making can be extremely difficult when there's a multitude of choices. So we have these guys that are just being wowed about Spotify's Discover Weekly. It was like when Discover Weekly was still quite new, right? Now everybody's used to Discover Weekly and all other features that Spotify offers. And of course, at the end of every year, we do our Spotify Wrapped, right? So how exactly does Spotify know you would like a song that you've never heard? How are you able to compute the recommendations so incredibly good that even when you leave your playlist on shuffle, all right, it just magically takes you, to right to the next song that kind of matches, and you're like, that's good, that's good, that's good. All right. It doesn't mean once in a while it doesn't veer off. Because tell me why I'm playing like gospel song, and then it's shuffling to other gospel song, and then before you know it starts gradually moving into something else I did not send it to. All right. But the key thing here is that for the most part and most of the time, even without you like tweaking anything, once you start from one or two songs, it just really can take you from there with the shuffle. And except if you are looking for something very, very specific, maybe you have a particular mood that you just want something very, very, very specific, except if that's the case, right? Most of the times the recommendations are just okay, or are just really good. Well, how does Spotify really do this, right? And again, I want to also highlight this aspect of choice overload. Many times those of us that work in data or work with data or build ML models, we always like to advise or tell people that, data will help you make good decisions, data-driven decision making, data aids decision making. Like we always like to throw around these words. However, even when you have really good data for decision making, all right, if there are so many options, then it becomes a problem. Sometimes we have what is called decision paralysis, or a decision overload, or a choice overload. Right? Consider when you go to a restaurant or an eatery and you want to get a meal, and they bring a very big menu to you. Right? I typically like when I go somewhere to eat and the menu is no longer than four pages at most. The moment you have menu that is getting to 7 pages or more, to be quite frank, I don't go too far into the menu. And instead, I would just rather ask um, the waiter or the waitress, what's your best seller? What are the most interesting dishes? So what am I doing in essence? I'm asking them now, even though I have the decision options, even though I have the variety, all right, I'm asking them to help me streamline the options to the best possible options. Why? Because humans struggle with choice overload. All right. If you give algorithms or computer systems a multitude of choices and you ask them to pick the best ones, you just need to, determine the policy function or the what do you call it, the optimization objective. Whether you want to minimize something or you want to maximize something, just define the objective, right? The algorithm will cook up something that matches or that reveals the best. But we are not algorithms, we are not machines. All right. So at the end of the day, we want to now have these systems able to do it for us. So the same way a waiter or a waitress would advise me with the best options to streamline my decision making so that I don't become overloaded and end up spending over an hour without even making a single order. The same way I would want a waiter to do that. The same way we also like when Spotify TikTok, Instagram, right, readily help us with recommendations, personalized because it matches our interests, it matches our specific needs, it matches our tastes, it matches our mood, right? It matches, the kind of thing that you want to hear at this point in time. So it removes that choice overload. So that's just pretty much, what really happens here. But what powers it, right? What sorcery is that? I decided to add this line because, to be honest, there's some people that take these things as some really magical things. It's just the same way people are taking AI or LLMs today. People who are not like technically inclined and who are not exposed to the data or AI field, people who don't even have basic AI literacy, when they see LLMs like ChatGPT, oh my God, they start, they say they've never seen anything like this before, right? And it's true, you've never seen anything like that before. So for a lot of people, it's like sorcery. All right, it's like this is magical. However, those of us that are at the forefront of the field or are building systems with these technologies, we keep complaining every day about the limitations. But the more we complain, the more people cannot relate with us because like, what is wrong with you? All right, it's like can't 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 anything satisfy you. So the truth is that it's not sorcery, right? It's powered by algorithms and machine learning. All right. So what exactly are we looking at here? So we start with a simple cluster, and this is where we're going to actually demonstrate it. So by the end of this tutorial, you should be able to build, in fact, you should be able to reproduce this diagram I have here because this is not just a random image from somewhere. This is actually an image from the data set or generated from the data set that I shared with you guys, right? So we'll start with this simple cluster. This cluster really is a cluster of songs in Spotify, right? So the original data set has about 200,000 plus songs. So we just took like the top 2,000. Actually, we can do 200,000, but it's going to take some time for the algorithm to fit to the data. That is, it's probably going to take maybe up to 20 minutes, depending on your machine. It's going to take like some time um, for for the algorithm to fit to the data. All right. So this particular image just shows like 2,000, or should I say 20,000 songs actually. So what we are going to do is that we're going to start from 200 songs, 2,000 songs, and 20,000 songs. In other words, we're going to start from um, 200 is 1,000 of the data sets, right? Then we'll take like 1/100 of the data sets, and then we'll take 1/10 of the data sets, and we'll fit the algorithm. The algorithm that generates or that generated these clusters is called the TSNE algorithm, otherwise, or in full, known as the T-distributed stochastic neighbor embedding. T-distributed is just coming from the statistical distribution of T-distribution, right? So when we continue with statistical methods later, especially for those in ML and LLM, we'll look at some of these distributions. For those of you that are in other fields, there's no need to dive too much into like what the distribution statistically means, right? But what you should just understand is that this is a type of algorithm that is used to generate embeddings. There are, of course, different embedding models, and every embedding model has, the algorithm that is used to generate it. Before I continue, I would like to quickly draw a point, and I think I like that this is a general audience for all tracks. So I want to quickly draw a point about algorithms and models. So I'll throw a question to the house, right? Can anyone point out what is the difference between an algorithm and a model? Because often we throw around these words and we assume that everybody knows, but I know that not everybody knows. And are they even the same? Are they the same? Are they different? Because I mean, there are times when this can be used interchangeably. So are they the same? Are they different? Feel free to raise your hand or drop a comment on the chat. Let's start with Favor.
Good evening, sir. From my understanding, an algorithm is basically a set of instruction that tells how code should behave in a certain way, while a model is very similar to an algorithm, but it learns based on data and patterns in data.
Okay, thank you for that. Now that you made that comment about steps for which a code should run, I want to further streamline the question by saying that what is the difference between an ML algorithm, not just a general algorithm, because the word algorithm is like can be very, very generic. So what's the difference between a machine learning algorithm and a machine learning model? So when I say machine learning algorithm, like for example, your logistic regression, think about that. So don't think just about code. Think about actual artifacts, actual, you know, actual mathematical or statistical models. So what would be the difference between a machine learning algorithm and a machine learning model? Okay, I'm seeing some. I would also quickly look at let me open our YouTube page and see if we have any comments there. So for those who are streaming live, feel free to live on YouTube. Feel free to drop comments on YouTube. Madam Larry says algorithms and equation. Okay. While model is a virtual representation. I don't know why I'm saying as if Olamileko has dropped one deep word of wisdom. But I mean, um, I like how you brought in that word equation, because sometimes we tend to forget that these things are actually mathematical expressions and equations. So that's Damilari, that's a good one. A model is an algorithm that has been fitted on data. Okay, close. If you are my interview, let's say you come and interview for a role on my team, and you give me this definition, I'll be more strict, right? But for the purpose of class and learning, I'll be a bit flexible. All right. Uthman says an algorithm is a step-by-step set of instructions or rules for solving a problem, while the model is the result after applying an algorithm to data. Okay. An ML algorithm is a mathematical set of rules used to learn patterns from data. That is from Woodwork. You have told us an algorithm Woodwork, but what about a model? Femi says an algorithm is in math, model is a data in action. Femi, you look like someone that speaks a lot to C-level executives and know how to convince them to drop 100 million naira for a project, a data science project. Femi, I don't look like someone that would know how to convince difficult stakeholders. You just use very simple, just break it down, very simple. It will even show some visualizations. And then they'll be like, wow, this guy knows what he's talking about. Definitely, we want to come and take our money. But yeah, that's a really good one. Maybe I don't look like. Oh, sorry. Let me mute this YouTube. Okay, so on YouTube we have Edidion. A model is an algorithm trained on data. ML algorithm is a procedural strategy used to design an ML model. Abiola says ML algorithm is a procedural strategy used to design a ML model. I like this class, right? Because I like you guys' choice of words. I can see strategy, I can see design. Hey, AI Code is dropping comments. So okay, this is Obina, guys. So in case you guys see a comment from AI Code, is Obina that is just dropping a comment. So Obina says an algorithm is a mathematical equation that maps inputs to outputs. A mathematical equation that maps inputs to outputs. Okay. A model is an algorithm that has been trained on data to perform a specific action. Okay, George, an algorithm is a step-by-step process to achieve a task. And the moment you say step-by-step process, you're already talking about the generic notion of algorithms. I want to streamline it to ML. Nelo says ML algorithm is a process of training a model while a model is the result of training an algorithm. You say training a model, then you not say training an algorithm. So which one are we training? Are we training a model or are we training an algorithm? All right. Algorithm is a process strategy to train the model, while model is the result of the algorithm. All right, so let me just summarize, right? You guys have made very beautiful points. I love all your answers, even if there are some that I've kind of tried to stretch, but indeed, an algorithm is a process of training a model. The model is a result of the algorithm. But let me further clarify that. So think about an algorithm as, again, as a process. So it's a process, all right? An algorithm is not an equation. Instead, a model is the equation. It is the model itself that is the equation. An algorithm is like when you are balancing algebraic equations in mathematics because you want to arrive at a particular answer. Maybe you want to arrive at something that says y equals x plus 2. But before you got to that point, on the left-hand side, there was both y and x terms. And on the right-hand side, they were like, maybe there was a number or another set of terms. So you want to arrive at a simplified version of the equation by having just y as the left-hand side, all right? So all those things that you guys did in high school, the process or the different steps you took in balancing that algebraic equation or simplifying the equation before you go to the final answer, that process is the algorithm. So you cannot say that that entire equation, all right, so it's a process. Now, I like to describe models as the products. So it's a process versus product thing. So the ML model is the actual product that comes out of it, right? So from the mathematical sense, the product is an equation, all right? But from the software sense, the product is an artifact. And when I say artifact, is that it's an actual object, right? It's an actual computed object. For example, we take that equation and export it as a Pico file, right? Or export it as any other type of file, file type. But basically, you now have it as an actual object that you can drop into an object storage or a file system. So what am I saying in essence? A model is a product. So whether you're looking at it from the mathematical or statistical sense as an equation, or you're looking at it from the software sense as an artifact, the point is that the model is a product, but the algorithm is a process that derives that product. All right. So for example, when you're doing linear regression, you have a lot of optimization steps. You do your ordinary least squares optimization, right? And you're optimizing an objective function in order to arrive at your optimal model, right? You are trying to fit a line or an equation to the data set. That is, you are trying to find what is the best orientation of this line or this curve on the data. The curve itself, that curve itself is a model. But before we started from a bare curve, y equals mx plus c. We don't know what the m is. We don't know what the c is. We just started from a simple placeholder curve. But over time, as we start adjusting the curve on the data and start saying, let me shift it like this, let me do it like this, let me move it like this. That process of shifting the curve iteratively until we find the best fit curve, that process is the algorithm. And usually ML algorithms are very well defined. There are steps, there are expressions, there are mathematical steps for that. But when we are now done, we now go from our bare y equals mx plus c to y equals 2.5x plus 0.135. What have we done? We've learned the values of m, the gradients, and c, the intercept. So in other words, we've learned the parameters that make our model best fit to the data. We've learned the parameters M and C that make our model or our curve best fit to the data. How did we learn it? We learned it by the algorithms. So that's why the algorithms are called learning algorithms. We don't say learning models, we say learning algorithms. But the model is a learned model or a trained model. So you don't train an algorithm, you don't learn okay, you learn an algorithm, but you don't train an algorithm. All right, you train a model. The model learns an algorithm. The model learns the steps. Once it has learned the steps and it has understood it, that's gotten fit to the data, it can then make predictions. I don't know if I am clear. Does it make sense? You know, I've used different words to describe what really goes on. So there are many different ways you can approach it from you know your simple high school math sense. You can approach it from the graphical sense, where you are actually visualizing a curve that is gradually moving across the data set until it finds a home. All right. So there are different ways to describe that. But the long and short of it is that the algorithm is a process, the model is a product, and that's very key. And that's why usually, I'd like to tell my team something very important when we are, when we're doing some of the work around building models. And I always emphasize on choice of words. The other day, I think it was the ML class, I was telling you guys something. That's for those in the ML class. I said that many people don't care about semantics. They feel like semantics is like you overdoing things. So they feel like I can just use any word as long as people understand. But you see, in ML and in any computational science, semantics can make or mar what you're trying to do. For example, about 6 or 7 years ago, I learned that you don't say that you are designing an algorithm if all you're doing is you're using sklearn, scikit-learn, or random forest, or an already existing algorithm. If you're using it, maybe if you're trying to write the code implementation of it. So you don't say you're designing an algorithm. All right. You are using an already designed algorithm. Somebody invented the algorithm. So the person who invented it designed it. So you're just using it. You're a user of the algorithm. Whether you have never seen it in code before, as long as it has been written in its bare mathematical form, you did not design the algorithm. So you don't design algorithms. Neither do you develop algorithms, except if you actually build the algorithm yourself. All right. Also, you don't design models or machine learning models. There are some things you can design. That word design has to be carefully used. You can design a training experiment. All right. You can design a learning algorithm, which, like I said, if you are building your algorithm from scratch, then you're the one who designed the algorithm. So yes, but you don't design a model. You develop a model, or you build a model, or you train a model, but you can design a learning experiment. You can design a feature a feature selection experiment. You can design a calibration mechanism, understand the probability distributions from the domain that generates that data set. All right. So these are some things you can do, right? But you don't design a model. So what do? You build a model, or you develop a model, or you train a model. Also, when it comes to the actual ML as a product that goes into applications, right? When you want to talk about the use of the word design, you say you design an ML system, or you implement an ML system. You don't implement a model, right? You don't design a model, but you design an ML system. You implement an ML system. You develop an ML system. All these different words can go when you're dealing with an ML system, because now you're dealing with a system. All right. So why? Because now you're dealing with a model as part of a software. So those particular engineering terms can now go. So choice of words are very key. I just thought to throw that out. All right. So I think I mean I like you guys' responses. So we'll just proceed. Now let us see how we can, of course, generate this particular visualization that we have um, on the screen here. Before I get to that point, what is really the essential thing that we're talking about here? Or what are we looking at? What's the essential underlying concept here? Because again, remember, we're talking about Spotify, and we're asking ourselves, what is the source tree? How did they do it? Right? Can we also do something like this? Like if we say we want to do a mock version of Spotify recommendation algorithm, can we actually do it? How can we replicate it? What exactly is going on under the hood? Right. So this thing that is going on under the hood is what I want to uncover a bit right? And having to without having to complicate this topic. So it's going to be as simple and approachable by everyone as possible. But what is really the essential concept here? The essential concept or the key notion here is a notion of representation. All right. How do we get recommendations? What does this visualization even mean? Because I've not explained the visualization yet. All right. What does it even mean? And how are we able to arrive at similar recommendations, personalized recommendations? The one word here is representation. Representation of complex things, whether it is music, images, words, whether it is videos, users in a particular, on a particular platform or in a particular network, right? We are representing these complex things. When I say complex things, they're complex because these are unstructured data. All right. These are not structured. They have different complexities. For example, take an image, for example. 1 megabyte of an image has 1 million, 1 million pixels. Because we're talking about 1,000 by 1,000 different units of that element. So you are dealing with something that has so many features, each pixel representing something very unique, a specific color code, a specific number representation of that image. And now you are not taking that entire 1 million just because you have it as a small looking picture. You might think it's not complex. It actually is very complex. So now, how do we now represent this complexity as points in a high dimensional space? A high dimensional space is just simply saying that I want to put this, I want to put this in a way that I can graph it or in a tabular form, right? So I want to have like different dimensions that represent this, this particular item. For example, the image now, we say, okay, let's have like multiple dimensions, and you can even have like 1 million dimensions, but 1 million is a lot. So typically we want to compress it. So maybe 512, 256, 128, and things like that. But the point is that we want to have actual numbers to represent the original items or elements. For example, words, right? Words are just a bunch of letters, vowels, and consonants. But when we want to model words, in order to be able to learn relationships, what do? Representation. In fact, the entire concept of machine learning is about representation learning. It's about learning representations from data. And that's why deep learning became very successful, because deep learning got so good. In fact, deep learning is what is designed originally to go as deep as possible into a particular piece of data to learn as many representations as possible that a traditional model, like a traditional tabular model, might not be able to capture. It's about capturing representations. So deep learning is like representation learning at its best, right? Because it goes layers and layers and layers deep into a particular data set or a particular piece of data to uncover features, to learn features of the data in order to be able to expose it. So it's about representation, really. Everything that makes personalization work is representation of a rather complex data set or data structure, right? But representation now in a numerical form as numbers or points in a high dimensional space. So when you see points, think of it as numbers. So think of a set of numbers, like numbers from like 1 to 10. Each number in that set is a point, all right? But when you have a set of 1 to 10, that set, right, is a one-dimensional set. So it just has one dimension, which means every single point or every single number in that set just has one thing that represents it. 1, 2, 3, 4, 5, 6 to 10, right? If I pick 7, that point 7 is just one thing, it's just 7. So the best I can do if I plot these points is to have a line. But what do I do when I want to have a better knowledge of the orientation of these points? And that's okay. What does this look like in a two-dimensional space? So a two-dimensional space would then give me two numbers for every point, right? So we are going from one number to two numbers for every point. Let me illustrate this a bit so that it doesn't look too abstract. I know I did not design that I didn't design that to be done here, but I mean, what's the fun? So I'll draw, I will just draw, or should I say I would outline two different sets here. And so we have a set A. Let me put this in equation form. I hope it's showing on the slide. So I'll put this in the form of equations. So just permit me and try and understand what we're cooking here, but it's going to make sense. So you have these sets 1, 2, 3, 4, 5. All right. This is just a one-dimensional space. A one-dimensional space is just called a line. Why? If I decide to draw a connection from 1 to 5, I'm just going to have a line. All right. It could be a straight line. It could be a curve. Obviously, 1, 2, 3, 4, 5 is going to be a straight line because there's no bend. It's just they're separated by equal number of steps. So there's no bend. So it's just going to be a straight line. However, I can have a second set that is represented or that represents each point with more than one number. So I have this set, and then I have a tuple each. All right. So maybe this one is 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. Guess what? If I don't want to guess, I want to throw this question. Let me increase the font of this a bit so that everybody sees it well. So I want to throw a question. I'll bring this up here. So it's just going to be by the side of motivations. All right. So I want to throw a question. In terms of the size or the length of each set, is there any of these sets that has more elements, or how do I put this? Like, which of the sets is longer or bigger in terms of number of elements? Feel free to drop answer in the chat. Okay. All right. So I think we have a consensus, right? They are equal. They're actually equal. B is not bigger than A. In terms of there's a different notion of big that would take us to like deeper into vectors. That's not what we're really talking about here. What we're really talking about here is not really bigness or magnitude. What we're talking about here is it's more like the length or the number of elements that we have. So for example, we pass A and B in Python and you say len of A is 5. If you say len of B, guess what? It's also 5. So both are 5 elements if you use the length function. But what is the difference? This is a one-dimensional space. So AKA it's a line. All right. 1 second. So AKA it's a line. However, this B is two-dimensional, aka it's a plane. It's still a space, so So a line is still a space. All right, a line is a one-dimensional space because space is a generalization. For most times, people always think that space starts from 3 dimensions, but space is just a general word. All right, just like when we come to vectors and matrices, right? A vector is still a matrix. It's just that it's a one-dimensional matrix. No, I don't want to use matrix. I want to use tensors. So ignore what I said about vectors and vector being one-dimensional matrix. A vector is a one-dimensional tensor, all right? And a matrix is a two-dimensional tensor. However, you typically start talking about tensors when you get 3-dimensional and above. So a matrix is just two-dimensional. A matrix is a two-dimensional array of numbers. But a vector is a one-dimensional array of numbers. And that's why this topic is about vector embeddings, because we're dealing with one-dimensional arrays, all right? So what am I saying in essence? This is a plane, and this is a two-dimensional space. Why is it two-dimensional? Because I can represent every single point in this set with two numbers. So if I now decide to plot a graph, in my graph, I can now have the x-axis, which is the first number in the point, or the first number that represents the point, and the y-axis, which is the second number that represents the point. I have just two axes here, or two dimensionals. Whenever we say x and y-axis, just think about it as, dimension 1 versus dimension 2. X and y is just that the thing that in mathematics was just like the general way to describe or start describing dimensions. And like I said, mathematicians like abstraction, so there's no need to be calling dimension when you can just say x and y. All right. So the moment we go from 2D to something higher, we are going to have a 3-dimensional space. So when we come here and we say C, then we want to represent this with 3 numbers each: 3, 4, 5, 5, 6, 7, 7, 8, 9, 9, 10, 11. Sorry. 1, 2, 3, 4, 5, 6. I mean, like in maths, you will still be able to graph what I just put down, but it's not going to be in the way I really want it. So let's preserve this order so that it looks like multiples, right? So there's a lineage between each of them. That's why I don't want to repeat. So point 4 will be 10, 11, 12. And then 13, 14, 15. So basically what I've just done here is that I'm ensuring that there's some sort of relationship between all 3 pieces. So this is 3-dimension, and it's a higher dimensional space. So this is where space comes from. There are different ways you can call this. You can call this a 3D space. You can call it a 3 space. All right. So and so on and so forth. Mathematicians have different ways of calling these different things, but let's just leave it as 3D, and hopefully everybody understands that. Right. So of course, by the time you start going to 4 and above, we start having hyperspaces, higher dimensional spaces, right? We start having things that mathematicians call manifolds. I'm seeing a comment. What is a tensor? A tensor is a multidimensional array of numbers. So multidimensional, it can be 1, it can be 2, it can be 3, an arbitrary number of dimensions is a tensor. So tensor is just a placeholder for this, can represent any number of dimensions, right? But if we're dealing with one line, it's a vector. If we're dealing with 2 lines, it's a if we're dealing with 1 dimension, it's a vector. If we're dealing with 2 dimensions, it's a matrix. And if we're dealing with higher dimensions, it's not just generally tensor, right? So representations is just about representations. So imagine if I now say, okay, I want to represent a picture in the form of this. That's basically what embeddings are about. So I want to represent a picture in the form of this, all right? So I'll say, okay, I have to decompose that picture into pixels. But because we have 1 million pixels, we have that many dimensions. All right. And so we say that it's a high dimensional space. High dimensional space is just like, it's just an arbitrary number. Is anything beyond 2, 3, we just generally call it high dimensional space, right? But in order to be able to properly compute different things in something that has like thousands of dimensions or millions of dimensions, we would typically represent them into a smaller dimension by compressing them. That compression is what gives you your embedding. Your embedding is like the final compressed version of the original data sets. So that we can then have something that is just as small as probably 3 dimensions, 4 dimensions, maybe 10 dimensions from hundreds or thousands. So the representation of complex things into high dimensional spaces allows us to quantify similarities. That is, we can have a quantifiable way to measure similarities. We can say that the similarity between object B, which maybe this particular object was a word originally. So we can say the similarity between object B and object C is 0.8, right? Because again, that's the best way that models can then start assigning maybe predictions or assigning categorizations to certain objects, or even predicting the next token like LLMs do. Because the large language models have to understand what word is the most similar to this sentence or these words we have written so far, right? And then it generates it. But it not only generates it in terms of similarity, it also has to look at it in terms of semantics. So semantics matter in machine learning, and especially machine learning that has to do with unstructured data, like images, music, words, sounds, video, audio, and so on and so forth. If you're dealing with text and tabular data, like your normal financial data, all those things where you just build simple predictive models, you might not be talking about semantics. Often you will not talk about semantics. But when we're dealing with very unstructured data, right, we then need to talk about semantics. Now, to be able to achieve this quantification of representations, to be able to model representation, to be able to represent complex things into a numerical dimensional space, we achieve that using vector embeddings, all right? And that's where, of course, that's what this topic is all about. In coming sessions, we're going to do more work with vector embeddings in vector databases, but it's essential that we have this foundation so that when we're talking about, load your embeddings from ChromaDB or from Quadrant, you will not go and be thinking, what exactly is even inside these embeddings, like inside these vector databases? You kind of already know what they are, what they mean, and to be very easy to work with them, right? If you're dealing with machine learning, like for those of us in the ML track, we will not work a lot with vector DBs, but understanding vector DBs are important because often, especially if you have like large volumes of data, and maybe you need to build recommendation algorithms, obviously you need to store numerical versions of those data somewhere. So I think for ML people, the notion of vector DB has been around. So we're going to do things that are still like vector DB related. It's just that you might not be using ChromaDB or any of these tools that applied AI or production AI guys are using. But you are already home to these notions because we'll deal with a lot with embeddings and things like that. So I talked about vector embeddings, all right. We are going to generate, the embeddings. So we're going to use a couple of steps to generate these embeddings. Particularly the embeddings for the particular data set that I have. I was thinking I had a slide on the steps. I think I must have accidentally deleted that slide. So, but in any case, at a glance, or let me just quickly create that here. How do we reproduce this particular visualization that we have here. So I'll do this first of all, and then we'll then go into VS Code. I'm going to just quickly write the steps here. So steps for generating stuff. I'll take my screen here. So I'll just be writing for the other. So the one is that we load data set from Pibowei. Oh, I really thought I had a slide. I accidentally deleted it. Okay, so I'm going to just copy this, bring it here. Right. I hope you guys are still with me, and I hope it's making sense. Is anybody lost? Or does anybody have any question that you need clarification on? Feel free to drop it on the chat if there's something that is not clear so far. So what's essential? Sorry, I'm in the wrong place. Wrong place. All right, so step one is that we load the data set from Cargo. Specifically, we load the Spotify data set from Cargo. That's step two. The second step is that we are going to use, this is download. We're then going to load the data into a pandas data frame. So I'm going to use pandas in this session. And the third step, we are going to select specific numerical features that quantify different attributes of music. Because again, why numerical features? Because we're trying to do we're trying to uncover similarity and semantic relationships. So we need a numerical way to represent it. So we are going to extract features that are numerical, which thankfully Spotify helps us to compute those features. Right. The original thing I wanted us to do before was we're going to go into the Spotify API. We're actually going to pull the data from Spotify API. But I realized something. I did not know this because last time I used Spotify API was last year. I realized that you can no longer, I had a whole slide on, let me show you guys, just so, it just gives you a taste of what would have probably done. So would have gone into Spotify, right? That was the original thing I really planned for this session. You go to your developer dashboard, you sign in, of course, you go to your developer dashboard, you create an API, you export, you copy your client ID and client secrets, you export that, and then we're going to interact with, the API in Python, all right? So what really went wrong? The problem was, as I was writing the code, I realized that Spotify no longer provides a particular feature called, what's that feature called again? Let me see. I have the original code. So they no longer provide a key feature that we require for these numerical attributes of dance, right? So for some reason they deprecated that endpoint, and as I started to search what was the problem, I realized that they had no reason to deprecate it. But I think they discovered that a lot of data was being harvested from that endpoint, and they didn't know a way to monetize it because it's a developer endpoint. So developers are using it to do like a lot of interesting stuff, but there's a lot of data there. And I think they didn't know how to monetize it. Of course, Spotify is it's not here for charity; they're here for business. So when they did not see how best to monetize it, they thought to deprecate it, which again doesn't make sense. From at least from the angle of like doing things for the developer community. So the name of that endpoint is audio features. Audio features are just like the numerical features that we require for computing different attributes of music. Spotify actually does that and provides that in that endpoint, audio features. But since that was not available, I had to go and look for the data sets because the beautiful thing about the technology ecosystem is that it doesn't matter whether you decide to deprecate something later, right? People would have archived whatever they could have found from the original, from what was available originally. So luckily, we're able to still have that same data set that has the audio features that we need. All right. So for that reason, we will not need to like go step by step into the Spotify API. We'll just use this available data set. So ideally, what we're doing here is that we're trying to select specific numerical features that quantify different attributes of music, right? So that we then use that to compute similarities. But something now happens after we've done this. The next thing that we need to do is that we need to, of course, we'll probably do some plots or whatever, but we then apply the TSNE algorithm. We apply the TSNE algorithm to learn embeddings from the audio features. Right, from these audio features, the ones that we have selected. So once we have applied the TSNE algorithm, right, we then have a model that understands, or should I say that has a model that is fitted to the data that is able to compute the similarity features, and then we can then visualize. All right. So we can then plot the cluster. And yeah, voila, that's pretty much it. So let's just get right into it straight up without any further ado. So I have a Jupyter notebook here. I'll share my screen so that we can just see that. I'll just reshare my screen. So fire up your Colab, your Google Colab, your VS Code, anywhere you can use a Jupyter notebook. Fire it up and let's dive in. Let's dive in. So, of course, the first thing you have to do is to select on the right here, select a, what do you call it? Select your Jupyter environment or your Python virtual environment if you already have one. If you don't, create one. Just call it, you can call it tutorial or anything you want to call it. That will make you remember. The packages that we need are just these particular packages, right? Ideally, you should install these on your terminal, but suppose you're using Colab or suppose you are in a different environment other than VS Code, and you're in a Jupyter notebook, then just do pip install, put that exclamation at the beginning. The data set on Cargo, I will drop the link here. The data set is Spotify, 1 second. Where's that data? Cargo. Spotify tracks, ultimate Spotify tracks. Well, let me drop the link. Someone raised their hand. Please go ahead. By the way, let me see if I already have this on Drive. I was trying to share you guys to share something on Drive. Yeah, if you raise your hand, just go ahead because I'm not really looking at the meeting now. Yeah, I'll just continue. So install, right? If you already have it installed, fine. You just pandas scikit-learn, matplotlib, and oh, by the way, add Seaborn, please. So Seaborn for visualize. I actually added this later because I didn't want to use I sort of changed my mind from just using default matplotlib for some of the plots. So if you've already loaded, I mean, wherever the path you have this from, if you are using Colab, mount the data sets. So the data set is Spotify features.csv. So if you're using Colab, just mount that data on your drive, right? Um, David dropped a some set of code for downloading directly from Cargo. So I don't know if David is here and you can drop that code again so that others can, for those who don't readily have the data set, they can just copy it and use. But if you already have it either mounted on your drive or if you're using VS Code and it's on your local, make sure you specify the path. Only specify this way if it's in the same directory of your notebook. But if it's not, if your notebook is in a different directory, please specify the full path, right? Then we'll just typically read the CSV. Is anybody doing this? Should I hold on a bit? Okay, I'll give like the next 2 to 3 minutes for installing this, mounting downloading the CSV, and if you're on Colab, mounting it. So I'll just wait for another 2 to 3 minutes so that you guys can just do that. Okay, are we good? I think 2 minutes has elapsed. Is everyone set now? Drop your reaction if you're set again. If you are not, drop a thumbs down. If you are still not set, if you are still trying, I don't want the one where you're not even trying, then you can't come and give me a thumbs down. I will chase you out of this class. But if you are still on it, then drop a thumbs down. Let me know. Okay. So okay, let me give you guys 2 more minutes. If you have a challenge, if the problem is that you're having a challenge, just drop a comment. Let's see if we can assist. If maybe you have a particular difficulty that you don't know how to actually proceed, you can just drop a comment so that we can assist. Let me look at the YouTube live if anyone is having any issues. So just give like another 2 minutes. Okay, we should be good now, right? How do we mount the data set using Colab? You drag the data set, you go to, you open your left panel. Is anybody here using Colab and has done this successfully? I can give you a 1 minute, 2 minute window to share your screen and just show it. Okay, David, please share your screen. Let me stop presenting. Or David, did you, sorry, were you trying to say another thing or you're answering my question? Oh, okay, sharing screen already. Please watch Femi and Victoria, please watch what he's doing. I don't know if David wants to speak because it's currently muted, but just in case you are not hearing anything, just watch the screen.
I've already mounted just an example of a particular data set here. So what you do is you just right click this place, click on upload, then you select the data sets that you want. You just double click on the particular data set and you should be able to mount it. So as you can see, I have this here. I don't know if I've been able to assist you on this. So you just copy the path. So you import pandas and the 5 parts. This. Then you can now see whatsoever you want. They have equals BD dots. Right. So I don't know if this has helped in a bit. Hello, were you able to get it?
Femi, did you guys see that? Did you guys see that? I hope you guys are able to reproduce it. Oh, perfect. All right, so I think we can proceed now. And thanks, David. You can stop sharing now. I'm just going to present. So back to the Jupyter notebook. All right, so let's come back here now. Of course, we import all these different things. Actually, I don't think we needed NumPy here, so it's just pandas. We're importing pandas as PD. They're importing TSNE from scikit-learn manifold module. Then of course PyPlots from Matplotlib and Seaborn. So I'll just put that here. I just ignored warnings because I was getting a warning from one of the source I ran. I would say that it's not really that important, all right? So I'll just paste the one that I needed. Again, let's also, a note of caution, please warning imports in production grade code. So this is just for iterations. Alright, so we read the CSV by passing the file path. Of course, you can define your file path just like David showed now. You can define your file path, right, this way. So you just pass the actual path of the file and then just do this. All right. Of course, the data frame, when you load this, you find that the data frame, and check the size, it has 232,725 items or rows or samples. All right. We do not wish to use all these 225. And that's where the subsetting comes. So we try to do a random sampling. So sample 200 of these samples, right? I'm adding a random state parameter here for reproducibility so that if anybody, because the thing with sample or random sampling from the word random, if you do random sampling, it's going to randomly select any 200 samples from the data, right? Although, yeah, I would say technically, I don't want to go into the nuances of Python and how these things work, but technically, it's not like it's entirely random, right? It's not like it's entirely random. Um, there's still an intrinsic choice of the randomization value, but it's not going to be reproducible across different machines. So we adding a random state is to ensure that the randomization is done in a reproducible way. So you can reproduce the exact same thing I have on my screen right now. So that's why we have the random state. So I would also put this in the charts. So basically, we're trying to get the subsets of the entire data set. We're trying to get 200 out of 232,725. Right. So this is like 1,000 of the original data. That's basically what it is. I mean, less than 1,000 of the original data. Now, we just do the dot head, which just gives us the first 5 rows or the first 5 samples. So this can give you like at a glance a view of the elements, the columns, what are the column names, right? Of course, if you want to see the column names at a glance, it's just which I believe some of us will be familiar with this. If you typically use pandas, they just your dot columns and then you see a list of your columns, right? So these are the columns that we have. Now you'll notice different types of columns here. You'll notice categorical variables, like the genre is categorical. We have country, soundtrack, reggae. We have these different categories. You have artist name. Artist name is not necessarily a categorical variable in that sense of having like a fixed number of classes, right? But of course, it's a textual variable. It's just a text. It's a bunch of words that you have there. Then you have track name, right? You have track ID. Of course, the track ID would most likely be unique elements. Then you have popularity. So these ones now are the numbers or the quantifiable features. All right. We have acousticness. It's an audio feature. So this is the beginning of the audio features, acousticness. We have danceability. Is this a danceable song? Can I wind my waist as I'm dancing this one? Right. There's a difference between when you're playing blues and when you're playing Afrobeat. Those of us that are like into music would definitely understand that a lot. And the duration is also an audio feature because the duration tells like how long. Now this has been specified for us as underscore ms. So which means that this is milliseconds, right? So it's a thousandth of a second. So 194,107 milliseconds would simply mean 194 seconds. So 194 seconds is just like 3 minutes plus. All right. This one is 102,000 milliseconds. So it's like 102 seconds. So it's less than 2 minutes because 2 minutes is 120 seconds, and so on and so forth. Then we have energy, we have instrumentalness. Then we have this key. We're not interested in this feature because it's a numerical feature, right? Even if we're interested in this, even if we can actually numerically encode this because it's a categorical variable, we can do, we can do a label encoding for this to convert it to a numerical value. However, we're not interested because we're interested in audio features. So this is liveness, this is loudness, this is speechiness, this is tempo. So those are the audio features. This is valence. So we take some of these features, right? We extract the features. Remember that the second in our slide, the third step for generating our cluster is to select the numerical features that we need. So we just take, actually, I'm going to remove popularity. I've changed my mind. I want to remove popularity from here. Should I leave popularity? Okay, let me leave popularity. Popularity is not necessarily an audio feature because it's not a characteristic of the audio itself. Popularity is just about like, you know, other people listening to it. But I'll just leave it. It doesn't really, it might not really change much. Then we have like at the end of everything here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 features here. So what I'm going to do, I'm going to copy this so that we can see. And what I do is that I'm going to subset my data frame, DF subset, by these features, which means I just want the data frame to only have these specific features that we have selected here. So let me drop that in the chat. Oh, you say the length of your data frame is different from the one I have. What's the length of yours? What's the length of yours? You can drop it in the chat. Let me know. So again, I would like to visualize. I would like us to see, not visualize. Sorry, I would like to show the data frame X. So we'll see what it looks like before we continue. Right. Oh, this is a NumPy array. Okay. Before I get to, it's already, we've converted it to NumPy array, so we're not going to see the data frame anymore. So let me just do it this way. We can see the data frame now. It's just the numerical features, right? Out of which probably the only one that looks odd here is popularity. Popularity is like a counting variable. It's more like an ordinal feature. It's still a numerical feature, but it's not a continuous feature, right? It's an ordinal variable. Others are continuous variables. All right, so you can see that they are decimals. So, but of course, by the time we do the dot values converts, dot values just isolates the specific element. So we're going to have a matrix, a NumPy array, which is a matrix. It's a two-dimensional, basically a two-dimensional structure that shows like the rows and the tables, the rows and the columns. Sorry. So every list item here represents a row or a sample. All right. So we have a nested list of each sample in the data. So once we've done this, we've extracted these values from these features. The next step is to apply the TSNE algorithm to reduce that to 2 dimensions. Hope says 101427. Well, it's either, I don't know if you're using Colab or something. Maybe somehow it has been truncated. To be honest, it's not really a problem. Even if the data set is just 20,000, what we're doing this night, everybody will get it, and you'll be able to make sense of it. I don't really think the size matters per se, right? Because again, we're not going to be using all the data for visualization. You're going to see why. So remember that we have subsetted the original data set. We have subsampled it to 200. Remember, we had 232,000 before. We're now working with 200. So you're going to see, like what that means in terms of the way the cluster would look, and in terms of even the speed of training the TSNE model, or should I say running the algorithm. So what I want to do here is I want us to time the operation for learning the task. It was not originally planned. I didn't originally plan to do this, but it's fun. So let's do it. So we're going to import time. So please add time to your imports. Add time to your imports. I want us to play around with something. We're going to check the time it takes to run the algorithms for different sample sizes. So we applied TSNE to reduce. Remember, TSNE is a compression algorithm. It reduces the embeddings. Sorry, it reduces the original sample size, which is you guys saw the original dimensionality, right? The original dimensionality is this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 dimensions. And then by the time you put it in an array form, we have this multi-dimensional array. If I want to see everything, it's going to be a loss because NumPy kind of truncates it. But I think if I print, it's going to It doesn't show you everything. Good. So I don't really care about seeing everything. It's truncated. But the point is, we now reduce it to 2 dimensions. So they are only going to be 2 dimensions. So what I want to do is, I want to now add time it takes to run the algorithm, right? So I would say, I'll start with start time. It's defined as time.time. Then I want to now determine, the length, the duration of running the algorithm. So I'll add a print statement here, and that's going to be an F string. So we fitted TSNA algorithm on the 200 sample data in so number of seconds. So we are now going to do the time minus start time, and we're going to show the answer in seconds. So that will give us the number of seconds it took to fit 200, to feed the algorithm on 200 samples, right? So we run this now. Let's see what it looks like. I'm also going to show you what the X2D looks like. You're going to see that it's just 2 dimensions. I'll paste this in the chat so that we can have it. So we're done. So if fitted the algorithm to 200 samples of the data in 13 seconds, all right? So it might be faster depending on if you are, if you are using a machine from outer space. So if your machine came from the alien world, maybe using an alien way now, maybe to be faster. Whatever it is, for 200 samples, this is what we have. Now let's look at what the 1 second. Let's look at what that X2D looks like. It's also going to be a NumPy array, but you can now see that it's just 2 dimensions. Every single sample just has 2 rows. Sorry, 2 columns. Every row in the data now has 2 columns. Remember, the original view was this. This row or this list item now has 11 items. In fact, let me put in data frame form. In data frame form, this is what it is. A single row has 11, right? So this is this vector has 11 points or 11 elements. We start from 45. All these other ones here are just the index positions. We're not counting them. From 45, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have reduced 11 dimensions. So I want you guys to understand the significance of this, right? The TSNA algorithm has reduced the dimensionality to 2. Why? Because we specify the number of components to be equal to 2. So the number of components, although by default, if we hover over this, we see that actually by default, the default is 2. All right. So, yeah. The perplexity, by the way, is related. I'm reading what is on the doc string here. So the perplexity is related to the number of nearest neighbors that is used in other manifold learning algorithms. Larger data sets usually require a larger perplexity. Consider selecting a value between 5 and 50. Different values can result in significantly different results. So ideally, perplexity is like an hyperparameter that has to be carefully chosen. The default value is 30. Right? Perplexity is just about how many nearest neighbors are we considering, right? In this algorithm, should we consider just 30 nearest neighbors? So anything beyond 30, in terms of nearness or distance, we should probably just start avoiding it as part of the cluster, right? That's a very simple way to explain that. Of course, random states, again, like I said, for for reproducibility, we select this random state. What that means is that the visualization I'm going to have when I show you the cluster, everybody's going to have the same thing. If you choose a different random state, right, then you would have something different. All right. So it doesn't necessarily mean that it will be different. However, setting a random state ensures that if any other person uses my code to run this model, they're going to have the exact same artifact that comes out of it. All right. So the model has been fitted. The model, the algorithm has been learned. Then we apply, of course, this TSN is the algorithm. We now apply it on the data set to transform the data set from 11 dimensions to 2 dimensions. And then we learn this in 13 seconds. All right. So the model learns in under 13 seconds. We're going to now come back later to change the number of samples to 2000 and see how long it takes. Right. But this is just for illustration purpose. So let's now proceed. We want to visualize this. So what we do is that we take these 2 dimensions. Remember, we have reduced 11 dimensions to 2 dimensions. We now want to add these 2 dimensions back to the original data frame, which is this. So we want to now create 2 new columns here and add those two dimensions that were the result of the compression of the 11 dimensions. Because now they are like new dimensions. However, they are dimensions that capture the original information in these 11 dimensions. So we've gone from 11 to a lower dimensional space, 2 dimensions. So that makes sense now. All right. So now what we're going to do is to add those 2 as additional columns now. So we're not creating that here. So df subset x, which means we are adding a new column. The column name is going to be x, right? It is going to now be this x2d. We're going to take the first value of each element. All right, so it's like saying that loop through this array. This is a 2-dimensional array. Every element in this array is a list of 2 elements, right? So loop through that. Fetch me every single list here, but for this first line, get me only the first value of the list. So it gives me the first value of the list. So that's everything I'm going to have in this new column X. So basically, it's going to be this, and so on and so forth until we get to this point for X. The second column is subset Y, and I'm saying look through the array. Every list in that array, give me the second element. So it's not going to be this until we get to the end. Are we together? Are we still together? Good. So we get the subsets, and now we go to the visualization. Never mind that you have seen the visualization. I can promise you that the plot we're going to have now will look different from this. But we're getting somewhere. Just relax. I can promise you that we have not cooked beans in this particular code. So this is the visualization that we have. It looks different from the one we had before, right? But this is because we have used 200 samples. Right, we have used 200 samples here. So what do we do now? Let's now go back to our original subset our original subsample. Let's increase the subsample to 2000. So we sample 2000, all right? Of course, we're still going to get the same head really because we're using the same random state, all right? Every other thing remains the same. The feature column remains the same, but when we do this, we now have 2000 rows by 11 columns. So there's a significant difference. So now the next thing I want to do is I want to copy. I want to like copy this cell. I don't want to use the same cell because again we're trying to look at the time it takes to run the algorithm. So now we're dealing with 2000 samples. All right. So how long would it take to fit 2000 samples? Have I created my X? Okay, I need to actually shift this away from here and just put it here instead. So so we're going to run this next cell. We're fitting 2000 samples, and I want to see how long it takes to fit. Obviously, it's going to take nothing less than 60 seconds. Nothing less than 60 seconds is what we are going to have. So while that is running, let me see if we have any comments. Hey there, I got an error. Value error could not convert string to float. Hey there, I mean, I don't know what your name is. It's just I'll just call you the ChatGPT way or the LLM way, which is what your name is. So I'm curious about what you ran that gave you this error. What did you run that gave you this error? Oh, you said yours took 16 seconds. Which one? The first one, the 200 sample, or the 2000? 2000. Ah, perfect. Okay. You are people using machines from outer space. My one is very primitive. I'm using a machine from the Stone Age. All right. So obviously, if 2000 took 16 seconds, it means that 200 will probably have taken maybe less than 5 seconds. Right. If your own 2000 took 16 seconds, it means, you know, 1.1 second. Sorry, 1.1 second, Anissa, for the 200 samples, right? Or was it for the 2000 sample? Okay, 200, good. I would have just ended this class. Like, I'll be too ashamed of myself. And if your instructor's code is taking 50 seconds to run for 2000 and the student is taking 1.1 second, I think the student probably needs to be able to take the class. All right. Jason said he was afraid. I was afraid too. Okay, so we have 2000. So the next thing I want to do is, of course, this is still going to be like two-dimensional as you know, as expected. Then we are now going to create the columns and then we plot. So plotting, you now see that there are more clusters this time around. So I mean, it looks like a particular beautiful mathematical theory coming together. Because look at now, the initial visualization, the first one was looking boring. Now it's looking like, hey, are we trying to have a pattern here? But never mind the curvature or the way this thing is looking like a river or whatever. Never mind. That's not really the important. The important thing here are the clusters. All right. That's like the most important thing here. Oh, the code for the graph. Sorry guys, I forgot to drop the code for the graph. So just to quickly go over the graph, I want to wrap up this session in the next 10 minutes. Just to go over that, it's just basically plotting functions. We plot fixed size 12.8, pass the data, we pass the x and y axis, which are the ones we want to really plot here, and then we vary it by the genre, because again we want to cluster by genre. So that's why we have the hue parameter. So this hue is just how we want to vary the data. It's sort of the how in which we want to how we want to vary the data in terms of comparing. We want to compare by genre. So we want to have different clusters and see, like, you know, different clusters look similar to themselves, and so on and so forth. So each genre now is going to come as a colored point. So all these colored points you are seeing here are just genres, and there, of course, here on the right here, you see the label for these genres. Yeah, so that's pretty much it. Now, what else? So let's move on to 20,000. In fact, before we go to 20,000, I want to make this a bit interesting. I want to fit the algorithm for 3 dimensions. And then you guys will see what it looks like. So obviously, the array will show 3 elements. All right. However, if we do this now, we may not necessarily be able to visualize this in this 2-dimensional way. So I think I'll skip that part for now because I don't want to have to go into like the 3-dimensional visualization. But this particular fit now will give us 3 dimensions. So ideally, we would have to add a third subset here and call that Z. So that would be the Z axis. So when we plot it, would ideally want to plot X, Y, and Z axis. Right. So I'll leave that one as an assignment, right, for you guys. So you guys will go and plot in 3 axes. TSNE correct. TSNE is similar to PCA in terms of dimensionality reduction. Actually, as a way of generating embeddings, PCA is also a useful way of generating embeddings by reducing dimensions. So yes, definitely similarities. That was a very good observation and a very good question. Would this be uploaded on GitHub? Yeah, it will be uploaded on GitHub for sure. Yes. I would also give you guys an assignment. So I'll put it up on GitHub and then I'll give you an assignment. Okay. And please remind me, guys, in case I forget, I want to show you guys something on the Google Classroom. For those who have not handed in the assignment yet on the Classroom, I'll show you guys how to do that. Yeah, David Alobo, you're right. The TSNE algorithm is faster than PCA. It's able to take advantage of GPUs more efficiently. Not just GPUs, but even using parallel threads. So I want to go back to this and now say 20,000. So again, we run all these different things. Difference now is that we're now fitting 20,000. And then I just simply add that here. We'll look at the time it's going to take to fit that. Obviously, I mean, if it took 50 seconds to fit 200, you can imagine that this machine will probably spend, 2 minutes or thereabouts to fix 20,000. Yeah. So I would. I would like to cancel this task. I don't want to do 3 dimensions. Okay, let's see. We'll do the 3 dimensions and we'll see what it looks like. I would visualize only 2, so it's just going to be the X and the Y axis that I would visualize. Let me see if we have any comments on the YouTube. Okay, no comments yet. I hope we're still together, and I hope it's making sense. Perfect. Has anybody done the 20,000 already? How many seconds was yours? Okay. So I think this was X and Y. Sorry, this one raised the hand. Yes, David, go ahead. David, are you speaking? You're muted. Oh, okay. It was an error. All right. So my Stone Age machine has refused to complete that. So I guess I guess I'll just move on. But you guys understand the point, right? So let's move on to the. Okay, David, you done the 20K. How long did it take? How long did it take on your end? I'll move on to 245 seconds. Okay, that's roughly 4 minutes. I'll move on to back to the slide. Roughly 4 minutes. Okay, so I guess when my one gets to 4 minutes, maybe to now behave itself. Is anybody still running it? Before I actually go back to the slide, is anybody still running? So let's know. Let me know if I should wait a bit. If you are still running the code, just signify with a reaction. So I know if we need to wait for a couple more minutes. I want everybody to have a feel for how this thing actually works in terms of code and visualization. Okay, so nobody is making a reaction, so I suppose that we are all good. Are we all good? Are we all good? Does it make sense? Okay, great. So yeah, so with congratulations on generating the cluster. If you got into 2000, you should be able to have something like this, right? Something like this diagram that I now have on the slide. So in case from the beginning you were confused about what exactly is this, where did it come from? That's your Spotify music embeddings, right? For 2000 subsamples of the data. So is the embedding clusters, or is the clusters from the embeddings that have been learned from the data sets? So the embeddings have been able to show similarity and semantic relationships between different musics, different tracks, different genres, and so on and so forth. So ideally, each isolated line or each isolated, because every line here has like different points, the different colored points. The colors just represent the genre, so the music that falls within that genre or that category, right? So a line is a cluster of all those different music sounds and genre that are similar to each other. All right, they're similar to each other, and they just get clustered, within a certain area or within a certain place. So when Spotify is making a recommendation to you, when they want to shuffle to the next song, suppose you are in this particular cluster now, all right? It would ideally want to shuffle across this across songs in this cluster. Okay, someone said 29 seconds. Mine is still running, so mine is on 5 minutes now. So 5 minutes is 300 seconds. So now, it's just about putting similar things within the same cluster, right? And then you begin to you notice that sometimes within a particular play period, so Spotify is taking you through different genres, right? However, they still have some similarities between them, and you would enjoy them because it matches your interests. Why does it match your interests? Because of learned embeddings. Does that make sense? So there are so many things that you can do with embeddings, right? My session is not meant to, I was tempted to add more things, cool stuff that we could do, right? Including some 3D visualizations, but you guys will look at embeddings, in the deeper contexts by next week. So next week we're having Casper. Casper is an AI developer advocate at Quadrant. So will be coming up next, is it Tuesday, Wednesday? It's going to be 2 p.m., 2 or 3 p.m. Watts our time. So please check it in the calendar. Just get ready. I know, some persons probably, if you're in the office, you might probably still be in the office, but if you can make out time for that session, it's going to be a great one. So Quadrant is an open source vector database. So which means that is something that you can readily use, so or we will readily use in our workflows. Typically, AISOC focuses more on ChromaDB, but I mean, once you understand how the vector database works, especially if you understand ChromaDB, if you choose to use quadrants, it's not really be a challenge as long as you really understand how they work. Or if you have learned quadrants first, which in this case we're going to learn quadrants first, by the time we come to ChromaDB, it's going to be like a lot easier. So for those in the production AI track, one of the things that we are going to be deploying is an actual vector database that you're going to be deploying as a service that your AI systems can interact with or can make calls to. So you connect to your vector database service, and then you're able to extract embeddings. So your vector database doesn't need to sit in the same VM or service with your AI system. So think of it like you can have them, working as a sort of microservices architecture. So if you're in production AI, you will learn like how you can actually go about some of those things. So if you're using vector DBs, whether you are using open source embeddings to generate the embeddings, loaders, whatever, you'll be able to do that. Yes, of course, you can use ChromaDB in production. At curriculum, we actually use ChromaDB in production. So we deploy ChromaDB, service in production, and we use it. It's lightning fast for generating embeddings. Storing embeddings and retrieval. Don't worry. If you're the production track, whatever that fault that you run into, you will deal with it when it's time. All right. So let's go on a bit. I've been talking about, well, we've actually done embeddings, like we've already done like all the interesting stuff, but we've not looked at the definition. So I wanted to save definitions for last. So because sometimes we start with definitions, it will look too abstract. But now that you have had a taste of it, what really are embeddings? Embeddings are dense, low-dimensional vector representations of data where similar things are close together. Sometimes when machine learning people throw around English, you think that they have solved world hunger. So you might be thinking that sometimes I've seen people listen to me that I said something and they were nodding their head in enthusiasm and excitement. And I know that they don't know jack about what I've said. But they're nodding their head. They're like, oh, that makes sense. It doesn't make sense. It doesn't make sense. I can promise you it doesn't make sense. Right? But not that people are too scared to feel like the dumbest person there. So maybe the speaker, the person who is speaking, probably the person speaking through those words and probably has no idea what he has just said. Hoping that nobody feels dumb enough to ask the question or ask a question. And because others listening, others in the audience don't want to feel like they are dumb or don't want anyone to think that they are dumb. They're like, that makes sense. It doesn't make sense. So what do we mean when we say embeddings are dense, low-dimensional representations, vector representations of data where similar things are close together? I think everybody understands that idea of, okay, similar things close together. But it's not enough to say embeddings are all about similar things close together. We have to really understand that they are low-dimensional vector representations. They are low-dimensional vectors. They are dense. So what does that mean? So I like to break things down, right? So a vector is an array of numbers. I've showed you guys from this illustration here, right? So it's just an array of numbers, all right? When we say a vector is dense, what we're simply saying is that the vector has few dimensions compared to the raw data or the original data where we are learning from. So it has fewer dimensions, and most of its entities are non-zero. As a way to help you understand this, when I say non-zero, right? In traditional machine learning, when we are preparing data, which for those in the ML track, in the foundations track especially, you get to learn. But if you're in the advanced track, like if you're in the engineering focus, right, which means you've done ML before, you would understand that when we are preparing data and we're creating features, there's something that we do when we're trying to represent categorical variables. Like maybe a particular categorical variable has things like maybe city. So maybe the variable is city and that's different cities. But of course, because it's categorical variable, it repeats itself a lot. We want to convert it to numerical representation. So what do? We say, okay, maybe there are like 7 or 10 cities. So we say let us do what we call one-hot encoding. So one-hot encoding kind of reshapes that one dimension into the number of categories that we have. So we originally had one dimension where it was just city, with all the different cities as the elements of that vector. We now say, I want to create more dimensions or more columns where every city is now a column name. So if we have 10 cities, it means we're going to have 10 different columns. Now, what that means is that when we get a particular sample, right, every element of the different cities take value of 0 until we get to the original city that particular element was supposed to be. That one now becomes 1. So every other element is 0 except the original city, the variable with the original city, or the variable that matches the original city from the original dimension. That one now takes a value of 1. What do you notice about this kind of data? If we take all the 10 dimensions and we visualize it, it's going to have a lot of zeros. All right. That lot of zeros, right? That lot of zeros, we define or we describe that, or the word for that is sparse. It is sparse, which means that it has a lot of holes or a lot of empty values or a lot of zeros. It has a lot lesser non-zero values than it does 0 values. So it's a sparse vector or a sparse matrix. All right. The opposite of that is dense. For example, if you recall our Jupyter notebook, when we created the 2-dimensional embedding vector, right? You can see that it's just a bunch of actual numbers, and there are no zeros. There are like so many different numbers. It's a wide range of numbers. It's a continuous range of numbers, right? And there are hardly zeros in it. So that's a dense vector. So when we say embeddings are dense, it means that you will hardly find zeros in this vector representation. It is dense. Does that make sense? Are we still together? Good. So, and unlike in one-hot encoding, which is a traditional vector representation, right, of a categorical data, in one-hot encoding, you are increasing the dimensionality of the data. So something that was originally 1 dimension and making it multiple dimensions in accordance with how many categories that the original dimension had. So we now create 1 column per category. So on the other hand, embeddings are reducing the dimensions compared to the original data. And so it is dense. So basically what you're having is an expansion versus compression scenario. Right? You're compressing the data. Like when you buy fresh agege bread, all right? Fresh one. And then you not take it. This illustration I'm making now is only Nigerians that want that. Maybe some West Africans in general will understand it. You now put the agege bread in between your 2 hands, your 2 palms. You now press it. You compress it. God help you if you find akara. Right? You buy it with akara, and you step it down with Sprite. Oh my God. Oh my God. So you compress it. Still the same data, but a compressed representation. You have reduced the dimension. And so it is now dense. Remember in physics, density is how much mass can you fit into a certain volume? That's density from the physics notion. In the same way, from the mathematical notion, it's about how much data can you fit into a lower dimensional space. That is why it's called dense. So when you say embeddings are dense vector representations, don't be confused. It is not sparse, it is dense. Why? It has been compressed. You will hardly find zero values. You're going to find a lot of values that have been packed into those few dimensions. Then when we say low dimensional, it means that we are compressing the original data into lower dimensions. So for example, in our TSNA code that we just walked through, we went from 11 dimensions to 2 dimensions. So the embeddings were generated from there are dense low-dimensional vector representations of the original musical data. So now this particular dense representation now has allowed us to now bring similar things close together and dissimilar things far away from each other. Does it make sense now? Are we still together? Okay. So, hey, please permit me and let us just wrap up with the next couple of slides. So key properties, right? Key properties, embeddings capture similarity. I've said this over and over again. When you hear embeddings, you think about vectors, but not only vectors, think about similarity. They capture similarity. Items with similar meanings or properties are vectors that are close to each other. We do this capturing of similarity by using some measurements to measure the distance between points or between items, right? We use distance measures like the Euclidean distance or the Manhattan distance or the Minkowski distance. Don't worry if I throw some buzzwords. We'll get to all those things, but not in this slide, all right? Euclidean might be a bit familiar, like some of us might be very familiar with Euclidean distance from the notion of Euclidean space, all right, in math. So Euclidean distance is just like a unit distance between two elements in, let's say, a two-dimensional plane, all right, or a three-dimensional space. So it's like you take a ruler on your graph and you just measure the centimeter distance between point A and point B, all right? So to further illustrate this, let us look at our graph, our points here. So the Euclidean distance between, if you look at the first vector, vector A, or the first set here, the Euclidean distance between point 1 and point 2 here is just 1. That is, there's just one step between them. So that's the Euclidean distance. All right. Point 2 and point 3, the distance is just a unit of 1. Again, I'm not using any specific unit. So I'm not telling you it is 1 centimeter or it's 1 meter. No, I'm just telling you that it's 1 unit. So unit is a placeholder for an arbitrary, we don't know the whatever, so we can choose the unit later. All right. In this case, we don't have a specific unit that we're working with. The only thing we're working with is here is just that we're just having different steps between the numbers. So there's just one step each in between them. So the Euclidean distance between each point here is just one step. All right. By the time we get to point B, it might be a bit different because now we are dealing with a two-dimensional space. So the way we are going to calculate the distance will not be by, say, like in set A, you just need to do 2 minus 1 to get the distance, or 3 minus 2, or 4 minus 3. Anyone, you get the same answer, 1. There's no mago to it. However, when we get to set B now, because it's 2 dimensions, we now have to be a bit, careful in the measurements, right? So we must take we now take a measurement that considers the distance between each member of the points, of each member of the respective points, right? Then we take the differences, we square the differences, and then we take the square root. So it's kind of square root of square the difference. But don't worry, this is not meant to shake anybody. We'll get to when we get to that part where we look at the actual mathematical representation of distance, we'll look into that. I just wanted to point that out. So basically, we're just talking about distance here, right? It's just like the distance can be measured in certain ways. You can use Euclidean distance. The choice of distance is also very important in terms of how we want to optimize the embedding, right? So we need to make specific choices of distance. Sometimes we use cosine distance, not even like linear distances. Sometimes we use angular distance. When we say cosine distance, we're not talking about angular distance, right? As opposed to a linear distance, like Euclidean. But cosine is angular, all right? So it encodes semantic relationships. So for example, if I say king, the numeric representation of king will be close to the numeric representation of queen. The vectors will be close to each other, right? The vectors will be close to each other. The difference between these vectors will only be with the notion that king is male and queen is female. That's where the difference will stand. So for example, if I take the vector of king, I subtract the vector representation, the vector, I subtract the vector of man or male from the vector of king. I'm going to be left with the vector of queen. Sorry, before I even get to that part, I will drop it in the comment because it's a bit tricky. Or let me put it on the slide. If I take the vector of king, I subtract the vector of man, and I add vector of woman or vector of female, I'm going to get the vector of queen. So let me put that on the slide very quickly so that nobody is confused. 1 second. So I'm going to take, I like to use these equations typesetting feature. Okay, so I just want to make sure that like nobody's confused about this. So let me put it here explicitly. So if we do vector, the vector of man, sorry, vector of king, it is the size of this. So vector of king minus vector value of man or vector representation of man and add vector representation of woman. What do I have? Or what do I get? I'm going to get vector representation of queen. So basically the difference between king and queen from the vectors, when you look at the numbers, when I say vector, you think about a set. Whenever I say vector of king, just think about the numerical values, the set of values you're going to have when we generate the embeddings for king. All right. So if I say vector of king minus vector of man, I've removed that gender component of the king. So it has now become genderless. So the vector has now become genderless. Right. So it's now a ruler. It's just now a ruler or a monarch. Then I now add the vector component of woman to that monarch vector. It now becomes a queen because now I've added the gender back to the genderless notion. Does it make sense? Does this calculation make sense? Okay. So it's like plus and minus, right? So like plus and minus. Just do some plus and minus and you get your answer. And to be honest, vector computations are just about arithmetics and some algebra, like plus minus multiplications, although vector multiplications. So it's not like it's just simple arithmetic multiplications or additions. It's now like you have to now bring in the vector machinery for that. But of course, embeddings make data usable for algorithms. Sorry about that. So they make data usable for algorithms. Why? Because you can now compute things faster. So imagine if you have to iterate over 1 million dimensions of data. Remember, dimensions are not rows. It's easy to work with 1 million rows. What am I talking about? People analyze data in terabytes and petabytes, right? So, and that's a lot of rows. That's a lot of rows. That's like millions to billions of rows, sometimes trillions of rows. So your Spotify is working with petabytes of data. So rules are not where the computational difficulties lie in. It is the dimensions, it is the columns, it is the dimensionality. And in machine learning, there's something called the cost of dimensionality, because we're talking about the computational challenges of working with high dimensional data. So the higher the dimensions, the slower computations can be. Thank God, of course, these days for deep learning and other variations of forms of deep learning that make computation easier and faster and high dimensional data. But one thing is for sure, when we generate embeddings from the original data, we cannot compute things faster. Even if your original data is a numerical data set, if it has so many dimensions, right? When you're building machine learning models, you would typically want to reduce the dimensionality of the data by either using PCA, TSNE, or any other dimensionality reduction algorithm, right? You decompose your data into fewer dimensions, and often you might want to generate embeddings for similarity measurements. So when your data has fewer dimensions, it becomes faster to compute. It also becomes more meaningful to represent that data semantically. So that's some of the benefits of embeddings, right? And then finally, how are embeddings learned? How are embeddings learned? So models learn embeddings by optimizing a task, like predicting context words in word2vec, reconstructing input in autoencoders. These are different algorithms, learning algorithms. And word2vec was a breakthrough in the 2010s, right? For pretty much predicting next tokens. Next token prediction is not really a new thing per se, right? It's just that large language models now have been able to scale it, right? So word2vec was the first breakthrough in terms of major breakthrough in terms of filling in the blanks. So given a sentence, what word should come into this blank, right? So sometimes you would train those models by masking some words in a sentence, some mask, and then the model learns how to, or like it learns how to predict what are most probable to fill in the gap. So the optimization process looks something like this. The model will start with random embeddings, that is random vectors or random numbers for the items. The items could be words, songs, images. Then in the training process, the model now begins to adjust these vectors to minimize the loss function. Remember that in machine learning or in an algorithmic process, what you're trying to do is to adjust a curve or adjust, in this case, vectors, right, in order to be able to best fit the data. So we're adjusting vectors that minimize a loss function. A loss function is just a measure of error. So we want to minimize the error. So the vector that has to the closest minimum of loss or error is the learned vectors or the learned embeddings. All right. Then after many iterations, the embeddings evolve so that items with similar rules or meanings end up close together in the embedding space. Remember, the embedding space is now the lower dimensional space that we have obtained from the originally higher dimensional space. Does that make sense? Then I'll just give an example with what embeddings, which is what I illustrated here with word2vec. There are other types of embeddings. There's embeddings for computer vision, like CNN-based embeddings, image embeddings, right? There are embeddings for for items like product items. So when you're on social media or you're on an e-commerce site, we have item embeddings. The illustration I'm giving here is just word embeddings, but we have item embeddings. The ones that are used for recommendation algorithms to predict songs or products, right? To predict user preferences pretty much, all right? So here we have word2vec and Glove. So let's say the task of the optimization, because again, a model will learn embeddings by optimizing the task. So the task here is predict missing words in a sentence. So you say the cat sat on the dash. how does the neural network or the model learn this right word? First of all, that's to learn an embedding or learn the embeddings. So the neural networks will learn the word vectors or the word embeddings that make it easier to predict the correct words. That's like the most simplest way to put this process. So the words that appear in similar contexts, like cat and dog, end up with similar vectors. That is like high level how that embedding process works. And so I think that brings us to the end of this session. I don't want to go beyond 7 p.m. So by the time I put this slide out, we'll also look at the other two examples, item embeddings and image embeddings. But I believe you guys get the point, right? So, and of course, embeddings play a very key role um, in machine learning, in data science, and of course, heavily it plays a role in large language models. And that's why this topic is for everyone, because everybody in all tracks work with embeddings. Whether you know how the embeddings work under the hood or not, you must work with it. Applied AI and production AI probably doesn't need to know the full intricacies, like the mathematical details of the embeddings, rather than just understanding that you generate an embeddings from maybe a document and what you are going to have numbers. And then we have a similarity measure that measures similarity between the numbers, so that when you ask a question, maybe you ask your document a question in the chat, you want to query your document, your question is converted to embeddings. So embeddings are generated from your question. The embeddings are sent to the vector DB to query the vector DB, so that it's saying that this is a question embeddings. Fetch me the embeddings from the document that are the most similar to this my question, by using your default similarity metric that was used to train the embedding. So maybe cosine distance, for example. So what now happens? The vector database now uses the cosine similarity measure to fetch the top n vectors that are most similar to the question, or most similar to the question embeddings. Then those embeddings are now fetched for you. Top n could be top 5, it could be top 10, depending on how many sources that you want, or how many similar embeddings that you want. And so it fetches it for you, and then you're able to do you're able to use it as context to answer your question. That's a summary of RAG, retrieval augmented generation. That's just pretty much a summary of RAG. It's about embeddings. Your RAG is all about embeddings, right? For applied AI, I'm going to come back next week. I think that will be my first session in applied AI. I'll do a RAG deep dive session after Casper's session on Tuesday. So you guys will see me like a little bit more often. ML people have been the ones enjoying me for the past 2 weeks. But in any case, I think that brings us to the end of this session. Embeddings are pretty much useful. I'm glad that you guys followed through. For those in the ML track, we will be continuing with the math. So I'm giving you guys a break. We'll come back to the math from Thursday, and then we'll hopefully look at some very interesting things, starting from distributions to probability distribution functions, a little bit of parameter estimation and things like that. Then we'll then come to some mathematical methods, and then we'll lay the foundation this week, then we'll come back next week to continue. But yeah, what else? I think that's pretty much it. So I will stop sharing now. If you guys have any questions, let me know. But I want to show you guys something on the classroom, on the Google Classroom. Like I said I was going to do this. So I noticed that some of you have not handed in your assignments on the classroom yet. So I will show you guys how to go about it, because I know a lot of people have filled the form and have submitted the form. But I would release scores on the form, but your grades will not reflect in the classroom until you hand it in. All right. So I'm going to come to respond to share my screen now. Where that's the how come I cannot see classroom? Okay. Yeah, you get my slides. All right. So I saw this comment. Good morning. For the assignment I submitted PT equals this. It was marked wrong, even though it's correct. Why did you say this is correct? Okay, yeah, it is correct actually. You didn't put your bracket, so I think I get your point. It's correct. So I'll release your score. For the submission, right? Obviously you are automatically marked, which means that even if you are correct, if you did not use the exact pattern that was expected in the answers, you marked wrong. So what I now do is that when I come to check your submission, I then check if you were actually correct, and then I release your score. So I will have to manually release scores for everyone. Now, if you're in the classroom, you are supposed to hand in your assignments here. You come to okay. I see some people have handed in theirs already, but not everyone has done that. So ideally, you're supposed to come and you're supposed to specifically come to this section, and then hand in your assignments. I'm wondering, okay, this is teacher view, so I don't even have the student view. I will not be able to show you exactly how you do that, but um, when you are done, I think what you just need to do is to indicate. I think what you just really need to do is to indicate that you uh, that you are done with the submission, which means most likely it might be necessary for you to attach okay, I think I see the thing now. Because this is a Google form, you're not able to make an attachment because um, it's not like you have a copy of that attachment. I just realized this. It's a different ballgame if I ask you guys to do an assignment elsewhere, maybe in a Python script or a Jupyter notebook, and then you come and hand over the Jupyter notebook. So that way, you come to you come here and then you attach the file. In this case, you're not attaching the file. So what you just do, just come and indicate, just hand it in, just indicates that you have submitted. So I would then look at your score in the Google form and then pass the score here. So I'm going to grade everybody here. So please, let's try and do that tonight, right? I think tonight is closing tonight, 23:59 watts. So it's just like in the next 4 hours, 5 hours, sorry. So please hand it in. So if you've not handed it, come and hand over your submission here. You don't really need to attach anything, it's just to indicate that you've done it, and then I'll grade you. Just wanted to point that out. Does anyone have any questions, comments? Okay, people are saying, mine is saying I don't have access. Are you on the dedicated plan? Because the classroom is exclusively for dedicated members. So if you're on the dedicated plan and you don't have access, it means that we'll probably need to resend you access, or I would ask that you check your email, maybe your spam folder for the invitation to the classroom. But I believe we have sent out invites to everybody. But I don't know if you are on the dedicated plan. Yes, that assignment was for the ML track. ML and LLM, not just ML and LLM. That was last week. So That was after our session last week. That assignment was for both the ML and the LLM tracks. Does that make sense? Okay. Any other questions, comments before we proceed? So the assignment is for everybody actually in favor, not just dedicated members. However, there's an extra step for the dedicated members. They will need to come and pass their submission on the classroom. Why? Because on the classroom, we're going to be able to aggregate grades and scores for everybody. All right. So if you are on the general group, you are still going to be able to do the assignment because the quiz form is open to everybody. And I'll be able to grade you on the Google form. The only thing is that it's going to be disconnected. Like if we have other assignments that are graded, it's going to be disconnected. I'm not going to aggregate grades. We generally not aggregate grades for like everyone on dedicated. So it's just going to be feedback per quiz or per assignment. But the dedicated group would have everything consolidated in the classroom. So let me drop the link for. Just give me a second. Let me drop the link on the chat. So on GitHub, you'll be able to see the. Okay, not just GitHub. I can actually drop you the form link. I'll drop you the form link as well. So you just use the form. But if you are on the, if you check GitHub, you'll be able to see it right there. You'll be able to see the, if you go to the ML or LLM track and you go to, I think week 1, you would see the assignment right there. So I think so far 20 people have submitted this assignment, which means that a lot of people have not submitted yet. So you guys still have, we still have more persons that need to submit. Okay, I'll drop the form link on the chat. All right. Any other questions, comments, feedback? Otherwise, it was great speaking with every one of you this night. And it was also great to see all the interactions. So I would see you guys in our next session. ML and LLM, our sessions continue tomorrow. Applied AI, I will see you next week. Production AI, production AI, maybe next week or per week. Production AI, maybe. So I would show my face once in a while in production AI. All right, guys, have a pleasant rest of your evening. Hoping I can stop. Yes, Rodia, go ahead.